Welcome to the Sleepy God. I'm so happy you found your way here. Whether you're settling in for a peaceful night's sleep, winding down from your day, or simply in need of a calming companion, you've come to the perfect place. Before we get started, I'd love to hear from you. The universe is a vast, mysterious place where the greatest forces of nature are constantly at work. Among the most enigmatic and powerful objects within this cosmic expanse are black holes, regions where gravity is so strong that not even light can escape. But how do these invisible giants come into existence? To understand the birth of black holes, we must first journey to the heart of dying stars, at the end of a star's life. Depending on its mass, a dramatic transformation occurs. A typical star like our Sun follows a relatively peaceful death. It sheds its outer layers to become a white dwarf, slowly cooling over billions of years. But for stars, with masses more than 20 times that of the Sun, their final moments are anything but peaceful. As their nuclear fuel runs out, the delicate balance between the outward pressure from nuclear fusion and the inward pull of gravity is lost. The star begins to collapse, its core shrinking under the weight of its own mass. This collapse triggers a spectacular explosion known as a supernova, one of the most powerful events in the universe. For stars that are massive enough, the supernova doesn't mark the end. It is merely the beginning of something far darker. The core that remains behind after the explosion continues its collapse, compressing further and further until, eventually, it reaches a point where not even the forces that normally resist such collapse, the pressure of neutrons, can stop it. At this point, space and time themselves begin to bend in unimaginable ways, and a black hole is born. Unlike regular stars, black holes are not made of matter in the traditional sense. Instead, they are defined by an event horizon, a boundary, beyond which nothing, not even light, can escape. What happens inside a black hole is one of the greatest mysteries of modern physics. It's not just a place where stars die, but where the very laws of nature break down, bending time and space in ways we cannot yet fully understand. Yet, despite their destructive origins, black holes are not malevolent. They are not monsters lurking in the dark, waiting to consume everything in sight. They simply are patient, powerful, silent, and in that silence, they carry with them a story not written in words or light, but in gravity itself. The birth of a black hole marks the beginning of a journey through the cosmos that is not immediately understood, but whose impact ripples across the universe. The process of collapse continues, reaching a stage where the black hole becomes a singularity, a point where density becomes infinite, and gravity reigns supreme. At this point, all the matter of the collapsing star has been crushed into an infinitely small space, and the known laws of physics cease to work. The equations that describe our universe fall apart at the singularity. What happens inside this point remains one of the deepest mysteries in science, a riddle wrapped in an enigma, where the fabric of reality itself is twisted beyond recognition. Despite all the darkness and incomprehensibility, black holes are not chaotic or destructive forces in the universe. They simply exist. They distort space and time around them, bending light and pulling matter into their depths. What might seem like a terrifying event is, in fact, just the natural result of the laws of gravity, pushing the universe toward its most extreme and mysterious states. To understand a black hole, we must first understand gravity, the force that governs the motion of everything in the universe. Gravity is the reason that we stay tethered to the Earth, the reason the moon orbits the planet, and the reason that planets move in elliptical orbits around stars. It is an invisible force that shapes the very structure of our universe. But black holes take this force to an extreme. They bend space itself, creating a gravitational well so deep that not even light can climb out, and so, the birth of a black hole is not a violent crash or explosion, but a quiet collapse, a slow death of a star that will give birth to one of the most powerful and mysterious forces in the universe. The black hole does not scream or roar as it forms. It is, instead, a silent architect of the universe, quietly shaping the space around it, creating a hole in the fabric of reality itself. What happens next is not just a collapse of matter, but a bending of the very rules that govern our universe. As the black hole begins to emerge, the space surrounding it curves in ways we have yet to fully comprehend. Its gravitational pull grows, stronger as it consumes the remnants of its star, drawing in dust, gas, and even light. And as it continues its journey, it becomes more than just a singularity. It becomes a key player in the grand design of the cosmos. Black holes are not solitary entities. They shape galaxies, alter the flow of time, and leave behind a legacy of their gravitational influence across the universe. In the quiet darkness of the cosmos, the birth of a black hole is but the beginning of a long and mysterious journey. Its story is just beginning, and the ripples of its existence will continue to spread across the universe for eons to come. And so, we are left with the questions. How do black holes influence the universe around them? What secrets do they hold within their event horizons? And what can we learn from their silent, patient existence in the vast expanse of space? As we turn our gaze away from the fiery birth of a black hole and toward the vast, dark expanse of space, we discover that black holes do not always travel alone. In fact, some of the most fascinating cosmic events occur when two black holes find each other, drawn together by the same forces that govern their existence. Gravity, imagine, if you will, two invisible giants drifting through the galaxy. Their masses are immense, each a remnant of a once vibrant star, now collapsed into a singularity, a point where the rules of physics no longer make sense. Yet, despite their silence, these black holes are far from inactive. Their presence is felt in the galaxies they inhabit, their gravitational pull altering the orbits of nearby stars and gas. These black holes, separated by unimaginable distances, begin an unlikely journey toward each other. But unlike the sudden, chaotic collision we might expect from such powerful objects, their meeting is a slow, patient dance unfolding over millions or even billions of years. This is not a rushed event. It is an inevitable spiral, a long, gradual approach dictated by the forces of gravity. At first, the two black holes are far apart, locked in orbits that seem to barely notice each other. But gravity, the invisible force that governs all things in the universe, has a plan. The black holes begin to move toward each other, slowly at first, their orbits stretching as the dance between them becomes more synchronized. Gravity pulls them closer, not in a violent rush, but in an elegant, silent waltz through space. As the black holes draw closer, their movements become more urgent. The space between them starts to shrink, and the rate at which they orbit one another accelerates. This acceleration isn't caused by any external force, but by the loss of energy as gravitational waves ripples in the fabric of space-time are emitted during their orbit. These waves are faint at first, undetectable by the human eye, but they carry away a tremendous amount of energy, forcing the black holes to spiral inward. Gravitational waves are an extraordinary phenomenon. Though they are far too weak to be heard with our ears or seen with our eyes, they are the silent messengers of the universe, carrying with them the stories of massive cosmic events. As the black holes lose energy through these waves, they get closer, their orbits tightening with every passing moment. This slow, relentless spiral toward each other continues for eons. The black holes may pass through several stages, each one marked by smaller adjustments in their orbits, each moment of their journey contributing to the gradual shrinking of their distance. As they get closer, the gravitational waves they emit become stronger, the frequencies rising like a crescendo in the cosmic symphony. It's as if the universe itself is holding its breath, waiting for the moment of union. Eventually, the black holes are no longer two separate objects. They begin to merge, their event horizons stretching and merging into a single, larger black hole. But unlike the violent, explosive collision we might expect from two such immense forces, this merger is a quiet and seamless event. The fabric of space-time is twisted, the paths of the black holes converging into a single point. There is no flash, no explosion, just the gravitational pull of two objects blending into one dot. In the final moments of their dance, the black holes release a final burst of energy, a ripple in space-time that spreads out across the universe, undetected by the naked eye, but carrying with it the echo of a cosmic story. The merger, though seemingly invisible, has left a profound mark on the universe, and this ripple, this gravitational wave, is the key to understanding how the universe works at its most extreme. For scientists, this is not just a story of cosmic forces at play, but a chance to peer deeper into the heart of the universe itself. These waves, so faint they are smaller than a proton, offer us a window into a world beyond our reach, where the very fabric of space-time is stretched and compressed in ways that challenge everything we know. As the two black holes spiral toward each other, the universe watches in silence, a vast, quiet witness to the most patient of dancers. In this slow, cosmic waltz, gravity draws them closer, their fates sealed by the unstoppable pull of space-time itself. And as they merge, they leave behind a gravitational echo, a signal that will resonate across the universe, telling a story of two giants, bound together by nothing more than the gravity they share. In the vast, nearly silent expanse of space, there are forces at work that cannot be seen or heard in the traditional sense. The most powerful of these forces, yet so faint they are imperceptible to human senses, are the gravitational waves' ripples in the very fabric of space-time. These waves, though invisible, carry with them the energy of some of the most intense and cataclysmic events in the universe. They are the subtle whispers of the cosmos, carrying the stories of black holes, neutron stars, and supernova across the vast stretches of space. The concept of gravitational waves begins with one of the most profound insights of Albert Einstein's general theory of relativity. Published in 1915, Einstein proposed that gravity is not just a force between masses, but a distortion of space and time itself, a curvature, much like a heavy ball placed on a stretched rubber sheet. In this model, massive objects like stars and black holes warp space-time, creating curves that dictate the motion of other objects. But the most remarkable part of his theory was the prediction that when massive objects accelerate, especially in an asymmetrical way, they send ripples through space-time, similar to the way a stone creates waves when dropped into a pond. These ripples, known as gravitational waves, travel outward at the speed of light, carrying with them information about their origins. The idea of gravitational waves was a theoretical, concept for many years, an elegant solution to the laws of physics, but impossible to detect with the technology of the time. The waves were expected to be incredibly weak, so faint that they would be almost impossible to observe. However, despite the difficulty, scientists believed that one day these waves would be detected. It wasn't until the detection of black hole mergers that the long-awaited breakthrough came. Gravitational waves could now be seen as more than a theoretical curiosity. They were the key to understanding some of the most dramatic and mysterious events in the universe. The first detection occurred in September 2015, when the Laser Interferometer Gravitational Wave Observatory LIGO recorded the faint but unmistakable signal of two black holes colliding more than 1 billion light-years away. The signal was brief, lasting just a fraction of a second, but its implications were profound. For the first time, humanity had heard the universe in a completely new way, not through light, but through the subtle stretching and squeezing of space-time itself. LIGO is an extraordinary piece of scientific technology, a pair of observatories located in Washington and Louisiana, designed to measure the most minute changes in space-time. The detectors work by using laser beams, mirrors, and highly sensitive instruments to measure any distortion in the length of their arms. When a gravitational wave passes through Earth, the distances between the mirrors change by a fraction smaller than the width of a proton. It's an incredibly delicate measurement, but with precise enough instruments, even the faintest of cosmic events can be detected. Gravitational waves, unlike light or sound, do not travel through matter in the usual way. They do not get absorbed by dust or scattered by other objects. They pass through everything undisturbed, stretching and compressing space-time as they go. These waves carry the raw energy of the cosmos, providing scientists with data about the masses, spins, and orbits of the objects that created them. But more than that, gravitational waves offer a window into the extreme environments of black holes and neutron stars, where the very nature of space-time is bent beyond recognition. The beauty of gravitational waves lies in their ability to offer information about the most violent events in the universe, events that are invisible in the traditional sense. A black hole merger, for example, would produce no light, no radiation, no outward signs of its existence. But the gravitational waves generated by the collision can tell a detailed story of the objects involved. Through these ripples in space-time, we can measure the masses of the merging black holes, their spins, and how they interacted with each other. We can even estimate the distance at which the event occurred, allowing us to peer into the distant past of the universe. And yet, despite their power, gravitational waves are subtle and elusive. The first signal detected by LIGO was so faint that it barely registered above the noise of the environment. It was only through the incredible precision of the LIGO detectors that scientists were able to identify it as something extraordinary. This discovery marked a new era in our understanding of the cosmos, one where we can hear the universe not through light, but through the very fabric of space-time itself. For astronomers and physicists, gravitational waves are more than just a tool for detecting black holes. They are a way of listening to the universe, of tuning in to the cosmic events that shape the very structure of reality. The waves themselves are not just faint disturbances. They are the echoes of the universe's most violent acts, carrying the memory of everything that has ever happened in their wake. As our technology improves, we will continue to refine our ability to detect these waves, opening up new windows into the heart of the universe. Each wave that reaches us, each ripple that passes through space, offers a glimpse into a universe that is constantly in motion, constantly changing, and as we listen to these gravitational waves, we are reminded that, in the vastness of space, even the quietest events can leave a profound mark on the fabric of reality. As the black holes continue their cosmic waltz, the inevitable pulls them closer. Their massive, invisible forms, once distant, now spiral toward each other in a slow, inexorable dance. This final inspiral phase is a process that can take millions to billions of years, but it is not without consequence. The very fabric of space-time is stretched and pulled by this ever-tightening orbit, releasing waves of gravitational energy that ripple out across the universe. In the early stages, this inspiral is almost imperceptible. The black holes, still separated by vast distances, move in slow, graceful orbits. The loss of energy due to gravitational waves is minimal, and their orbits change only slightly with each passing cycle. From a distance, the black holes might appear as distant, silent objects, locked in their slow and deliberate dance, unaware of the immense drama unfolding in the depths of space. But as time passes, their orbits shrink. The black holes draw ever closer, their movements more urgent. The loss of energy intensifies, and the gravitational waves they emit become stronger, louder, rippling outward with increasing frequency. These waves are the cosmic heartbeat of the merger, a series of faint signals, each one a whisper of the immense power at play. They carry with them the story of two black holes, once separate, now bound in an ever-tightening embrace. As the black holes draw nearer, their speeds increase. The once languid motion becomes more frantic, more desperate. The orbits tighten with every passing moment, and the black holes approach one another at a fraction of the speed of light. The forces at work are staggering. Every loop they make, every revolution they complete, brings them closer to the final, inevitable moment of merger. This final Inspiral is not just a matter of gravitational attraction. It is a dance of decay, a slow erosion of the black holes' once stable orbits, driven by the loss of energy in the form of gravitational waves. With each loop, they lose a tiny fraction of their energy, each loss pulling them ever closer. It is as if the universe itself is holding its breath, waiting for the inevitable moment when two of the most powerful forces in the cosmos will collide. And then, the crescendo, the moment when the orbits become so tight, so rapid, that the black holes are no longer two distinct objects. They become a single system, a united force of gravity. Their identities blurred as they spiral inward toward each other at speeds approaching the speed of light. The gravitational waves that ripple out at this stage are stronger, sharper, their frequencies rising with each orbit. It is as if the universe itself is amplifying the signal, the final call before the moment of merger. For the black holes, there is no turning back. As they close the gap, their final orbits become more elliptical, a perfect cosmic death spiral. The energy they release in these final moments is nothing short of astounding. In a fleeting instant, the two black holes emit more gravitational energy than all the stars in the observable universe combined. Yet this outburst of energy is silent, invisible to the naked eye, and only detectable by the faintest of cosmic instruments. What is remarkable about this inspiral phase is its incredible regularity. Even as the black holes draw closer and their orbits quicken, they continue to follow the laws of general relativity. The patterns of their movements are predictable, the frequencies of the gravitational waves forming a consistent, easily identifiable signal. This provides scientists with a unique opportunity to study the very nature of black holes, their masses, spins, and the forces that govern their behavior. In many ways, this Inspiral phase is the ultimate testament to the power of gravity, not just as a force, but as a sculptor of space-time itself. The orbits of these black holes are not merely a result of their mass. They are the natural consequence of the bending and curving of space-time, an elegant dance that continues until the final moment. The Inspiral does not last forever. At some point, as the black holes approach their final moments, the signals become so intense that they become the focus of detection. The chirp of the gravitational waves grows louder, the frequencies rising in a beautiful crescendo that marks the final moments of their union. This is the point of no return, when the black holes are so close, so tightly bound, that nothing, not even their immense gravity, can keep them apart. And so, as the black holes reach the brink of merger, they leave behind a trail of energy, a legacy of gravitational waves that will stretch across the cosmos long after the event itself. Their dance of decay, once slow and imperceptible, has now become a cosmic performance, one that will be remembered in the echoes of space-time for eons to come. And then the moment arrives in the quiet darkness of space, where sound does not travel to black holes. Silent, invisible giants finally merge into one. The space between them vanishes in an instant, collapsing under the weight of their immense gravity. For a brief, fleeting moment, everything in the universe pauses, as if holding its breath. There is no explosion, no flash of light, no dramatic cosmic explosion to announce their union. The universe, in all its vastness, holds its silence. The merger is a seamless event. The two black holes, once separate, now become a single, larger black hole. In their final moments, they converge, their event horizons stretching and merging into one. There is no violent rupture or flash of heat, only the quiet bending of space-time as the black holes collapse into one unified point. The process is governed entirely by the laws of gravity, and as such, it is not a chaotic or explosive event. It is a process that follows the natural flow of space and time. The silence of this moment is almost incomprehensible, a silence so profound that it seems to embody the very nature of black holes themselves. As the black holes merge, a tremendous release of energy occurs, but it is not visible to the eye. Unlike other cosmic events, such as supernova or gamma-ray bursts, which emit bright flashes of light, the energy released in a black hole merger does not manifest as electromagnetic radiation. Instead, it is carried away in the form of gravitational waves, ripples in the very fabric of space-time that spread outward across the universe. These waves, though invisible and undetectable by the human senses, carry with them the signature of the merger. The energy released in the final moments is staggering, more powerful than the combined output of every star in the observable universe. Yet it is completely silent. For the first time, humanity has been able to hear these cosmic events, not through light or sound, but through the stretching and compressing of space-time itself. The waves that ripple outward from the merger are faint at first, but as they travel, they carry with them the story of the collision. They tell us the masses of the black holes, their spins, and the details of the final moments of their union. And through these waves, we learn that what we once believed to be the most violent and chaotic event in the universe is, in fact, a quiet, elegant moment of cosmic convergence. Despite the profound impact of the merger, there is no flash of light, no outward display of energy to mark the event. The only indication that something has changed is the subtle distortion of space-time itself. As the black holes merge, Their gravitational pull distorts the space around them, bending light and altering the paths of nearby stars. For those distant observers, the merger would appear as a gentle ripple in the fabric of reality, a quiet moment in the vastness of space, and yet the merger does not mark the end of the black hole's influence. Once the black holes merge into a single, larger black hole, the ripples continue to spread outward, carrying with them the echoes of their cosmic dance. The gravitational waves that were generated during the merger are not just a fleeting phenomenon, they are a lasting imprint on the universe, a signature of the event that will continue to resonate for eons to come. The moment of merger, though, quiet and seemingly without fanfare, is one of the most profound events in the universe. It marks the culmination of a journey that began billions of years ago, with two massive stars collapsing under their own gravity. Through their death, new life is created, not in the form of visible light, but in the form of gravitational waves that ripple through the cosmos, carrying the memory of the black hole's journey and their final, quiet union. The silence of this moment is not an absence, but a presence that speaks of the universe's most extreme and powerful forces, bending space and time, creating new chapters in the cosmic story. The merger of two black holes is not a chaotic crash, but a graceful, inevitable moment where gravity pulls two giants into one, and in the silence that follows, the universe whispers its story to those who listen. After the black holes have merged, the new creation, a larger, unified black hole, is not immediately settled. For a brief moment, the newly formed black hole quivers, shaking off the chaos of its violent birth. This is the Ringdown phase, an elegant and transient event where the black hole smooths out the distortions created by the merger. Imagine the sound of a bell being struck. The vibration rings out across space, and as the sound gradually fades, it carries with it the last remnants of energy from the collision. In the case of a black hole merger, this ringing is not a sound at all, but a stretching and bending of space-time itself. These vibrations, known as gravitational waves, slowly fade away as the black hole reaches its final, stable state. The Ringdown is not just a brief moment of calm after the storm. It carries with it the echoes of the cosmic event that has just unfolded. These gravitational waves, while subtle, contain profound information about the new black hole's characteristics, its mass, spin, and the precise dynamics of the merger. The shape and frequency of these waves allow scientists to measure the details of the black hole with extraordinary accuracy, shedding light on the extreme physics at play. During the Ringdown phase, the newly formed black hole undergoes a process of settling, where it smooths out the uneven distortions created by the merger. It's a moment of cosmic grace as the black hole stabilizes and becomes a more predictable, spherical object, devoid of the chaotic fluctuations that marked its birth. It is as if the universe is giving the new black hole a moment to find its equilibrium, to emerge from the turmoil of its violent union and take its place in the cosmos. Though it may seem like a quiet moment in the universe's story, the Ringdown phase is crucial. It is the last step in the merger process, the final adjustment that allows the black hole to stabilize. And in this stillness, the Ringdown waves carry one last message. The merging black holes, though gone, leave behind their legacy a signature that will echo through space-time. For as long as the universe exists, these final moments are particularly fascinating because they test the very limits of our understanding of physics. As the black hole settles into its new form, the waves it emits provide a unique opportunity for scientists to test Einstein's theory of general relativity in extreme conditions. The characteristics of the waves, how they fade, how they spread, can reveal whether gravity behaves exactly as we expect under such intense conditions, or if something more exotic is at play. In a way, the Ringdown serves as a cosmic fingerprint, telling scientists everything they need to know about the newly formed black hole. By analyzing these waves, physicists can deduce the precise characteristics of the black hole, including the masses of the original black holes that merged and how they spun before their union. This process, though subtle, is one of the most powerful tools available for studying black holes, allowing us to peer deeper into the heart of these mysterious objects. But while the Ringdown is a moment of settling, it is also a reminder of the forces at play. The energy released during the merger is staggering, but it does not dissipate in a flash. Instead, it is carried away by gravitational waves, stretching the very fabric of space-time, leaving behind only the faintest echoes of the most violent event in the universe. In these quiet moments, we learn that the universe does not always announce its most profound moments with a loud crash. Instead, it whispers in waves, its secrets slowly unfolding across the cosmos. As the Ringdown fades, the new black hole settles into its final, stable state. The echoes of the merger will continue to ripple through the universe, a testament to the cosmic forces that shaped it. In the silence that follows, the universe continues its endless journey, carrying with it the memory of two black holes once separate, now forever united in a cosmic embrace. Though silent in the traditional sense, the merger of two black holes speaks volumes through the subtle ripples it creates. These gravitational waves are the true messengers of such cosmic events, carrying with them the secrets of the universe. Each wave, as it passes through space-time, carries profound information about the black holes themselves, their masses, spins, and how they danced through their final moments before merging. For scientists, the detection and analysis of these waves have opened an entirely new frontier in the study of the cosmos. Unlike traditional methods of observing astronomical objects, which rely on electromagnetic radiation, light, radio waves, X-rays, etc., gravitational waves allow us to hear the universe. This new way of listening has completely transformed our understanding of black holes, offering insight into their nature in ways never before possible. The LIGO detectors, located in Washington and Louisiana, are the primary instruments used to detect these faint gravitational ripples. By measuring the tiny distortions in space-time, LIGO has opened a window into the extreme conditions near black holes, a place where gravity reigns supreme and the rules of physics bend in unimaginable ways. When a gravitational wave passes through Earth, it causes a minuscule distortion, a change so small that it is smaller than the width of a proton. To detect this, LIGO employs incredibly precise laser interferometers that measure the distances between mirrors set kilometers apart. When a gravitational wave passes, the distance between these mirrors changes, revealing the presence of the wave. The challenge, of course, is that these waves are extremely weak. Most of what LIGO detects is noise, vibrations from the Earth's surface, wind, even passing traffic, but every now and then, a gravitational wave signal cuts through the clutter, sharp and distinct. The first time LIGO detected a signal from a black hole merger in 2015. It was a momentous event in the history of science. A faint chirp, lasting only a fraction of a second, signaled the merging of two black holes. The signal was so weak that it barely registered above the noise of the environment, but its implications were profound. By studying the characteristics of the wave, its frequency, amplitude, and how it changed over time, scientists could deduce the properties of the merging black holes. This was not just an accidental discovery. It was a moment of clarity, where theory and observation met in a way that confirmed many of the predictions made by Einstein's theory of general relativity. The collision was exactly as general relativity had predicted it would be: two massive black holes spiraling toward each other, merging in a burst of gravitational energy that would reverberate through space-time. Each gravitational wave detection provides scientists with a wealth of data. By measuring the changes in frequency and amplitude of the wave, researchers can determine the masses of the black holes involved, the spin rates, and even the distance to the event. The waves themselves act as a sort of cosmic fingerprint, each one unique to the event that created it. For instance, the frequency of the wave increases as the black holes spiral closer together, and as the merger occurs, the wave reaches a peak before fading away. This rising and falling of the wave's intensity, known as the chirp, is a distinctive signature that allows scientists to distinguish between different types of mergers. In a sense, gravitational waves provide a snapshot of the universe's most extreme events, captured in the fleeting moment of their passing. But beyond just understanding black holes, these waves are a key to unlocking even deeper mysteries of the cosmos. By analyzing the properties of gravitational waves, scientists are also able to test the very fabric of space-time itself. Are Einstein's equations still valid in the face of these intense gravitational forces? Do black holes obey the same laws that govern smaller, less extreme objects? The study of gravitational waves allows us to probe the universe at its most fundamental level, but there is more to this discovery than just confirming theories. Gravitational waves may also open the door to entirely new kinds of physics. The faint distortions that travel across the universe carry with them information that electromagnetic radiation cannot. For example, gravitational waves allow scientists to observe black holes that are completely invisible in other wavelengths of light. Traditional telescopes, like optical and radio telescopes, cannot detect the light emitted by black holes, as they do not emit visible radiation. But gravitational waves do not rely on light. They are sensitive to the most extreme regions of space, where time itself is distorted, and where light cannot escape. As our technology improves, so too will our ability to detect these waves from more distant and fainter events. Future observatories, like the space-based LISA detector, will be able to capture gravitational waves from even more extreme sources, such as the mergers of supermassive black holes at the centers of galaxies. These observations will not only provide a clearer understanding of black holes, but may also reveal entirely new phenomena, such as exotic objects or dark matter, that we cannot detect with traditional methods. What is truly remarkable about gravitational waves is their ability to tell a complete story of an event that is otherwise invisible. They allow us to study the universe's most violent events, not through light or sound, but through the very fabric of space-time itself. Each wave carries a unique signature, each one revealing the story of its origin. And in this quiet, subtle form of communication, the universe speaks to us, telling its tale in waves that ripple through space, leaving behind clues that scientists are just beginning to understand. And as our ability to decode these waves advances, we come closer to unlocking the deepest secrets of the cosmos. Each gravitational wave, no matter how faint, is a message from the past, a whisper from a distant black hole merger, a reminder that the universe is far more intricate, far more connected than we ever imagined. To truly understand black holes, one must confront the most mysterious part of these cosmic giants, the event horizon. It is the point of no return, the invisible boundary beyond which nothing can escape. Once an object crosses this threshold, it is lost to the outside universe, its fate sealed by the immense gravitational forces at play. But what exactly happens inside a black hole beyond the event horizon? The event horizon itself is not a physical surface. It is a region in space where the escape velocity, the speed needed to break free from an object's gravitational pull, exceeds the speed of light. The most startling aspect of this is that since nothing can travel faster than light, nothing can escape once it crosses the event horizon, not even light. Hence, the black hole appears black, a perfect sphere of darkness that absorbs all matter and radiation that dares approach. The exact nature of what happens within the event horizon remains one of the greatest mysteries in physics. According to general relativity, the gravitational forces inside the event horizon become so extreme that they warp space and time to an unimaginable degree. The core of the black hole, known as the singularity, is where the curvature of space-time becomes infinite and the laws of physics break down. In this strange, otherworldly place, the concept of distance, time, and even matter loses its meaning. This concept of the singularity is one of the most perplexing in modern physics. It is a point where density becomes infinite, where an entire star's worth of mass is squeezed into an infinitely small space. There are no measurements, no structure, no substance in the conventional sense. The singularity marks the boundary of our understanding of the universe. It is a place where known physics, based on the principles of general relativity, cannot explain what happens. However, just because we cannot observe it directly doesn't mean that black holes don't affect the universe around them. The space-time distortion that occurs near the event horizon can have dramatic effects on objects outside the black hole. For example, light from distant stars can be bent and distorted by the gravitational field of a black hole. This effect, known as gravitational lensing, occurs when the black hole's immense gravity bends the path of light, creating arcs and distortions of the light coming from behind it. In fact, this bending of light can be used to detect black holes. Even though we can't see a black hole directly, we can observe how its gravitational pull warps the light of stars and galaxies behind it. Through this technique, astronomers have been able to identify the presence of black holes in distant galaxies, even though they remain invisible to traditional observation methods, while the singularity inside the event horizon remains a place of extreme mystery. There are theories attempting to explain what might be going on. Some physicists suggest that quantum mechanics, the science that governs the behavior of particles at the smallest scales, may hold the key to understanding the singularity. It's possible that a new theory of quantum gravity, one that unifies general relativity and quantum mechanics, will be able to explain the strange behavior of black holes at their core. One theory proposes that rather than an infinitely dense point, the singularity could be a region where space and time are so warped that they form a bridge to another universe or two different regions of space-time. This theory, which is often discussed in terms of wormholes, suggests that black holes might not be destructive in the traditional sense, but instead could act as portals, gateways to other parts of the universe, or even to parallel universes. While this idea is still highly speculative, it speaks to the profound mystery of black holes and the potential for discoveries that challenge our understanding of the universe. Despite these wild speculations, the truth remains that we don't yet know what happens inside a black hole. The boundary at the event horizon marks the limits of our current understanding, where our best theories of physics break down and leave us with nothing but questions. But in that uncertainty lies the allure of black holes. They are cosmic laboratories, places where the most fundamental laws of the universe are tested and stretched beyond recognition. The beauty of the black hole's event horizon lies in the paradox it presents. Though we can never see inside, its existence forces us to rethink everything we know about space, time, and gravity. In the silence of the event horizon, we are reminded that the universe has depths far beyond our comprehension. Black holes are not just celestial objects. They are cosmic mysteries, waiting for us to uncover their deepest secrets. As we continue to observe and study these strange phenomena, one thing becomes clear: the more we learn about black holes, the more we realize that the universe is far stranger and more complex than we ever imagined. The event horizon is just the beginning of that journey, a threshold to a realm where the ordinary rules of nature no longer apply, and where the most extraordinary mysteries lie in wait. While stellar black holes are born from the collapse of massive stars, another class of black holes, far more massive and enigmatic, lies at the centers of galaxies. These are the supermassive black holes, whose masses range from millions to billions of times that of the Sun. Unlike their stellar counterparts, supermassive black holes do not form from the collapse of a single star, but rather they are thought to grow over billions of years by consuming surrounding gas, dust, and even smaller black holes. Their existence at the heart of galaxies is one of the most puzzling and fascinating mysteries in astrophysics. Almost every large galaxy we observe contains a supermassive black hole at its center, and the Milky Way is no exception. At the heart of our galaxy lies Sagittarius A*, a supermassive black hole with a mass around 4 million times that of the Sun. While it is relatively quiet at the moment, not actively consuming large amounts of matter, it still exerts a powerful influence over the galaxy. These supermassive black holes play a critical role in shaping their galaxies. They serve as the gravitational anchors around which stars, gas, and other cosmic materials orbit. The immense gravity of a black hole governs the dynamics of the surrounding stars, keeping them in motion and influencing the overall structure of the galaxy. In fact, the orbits of stars at the galactic core are controlled by the black hole's gravity, and the distribution of matter in the galaxy can be traced back to the actions of these cosmic behemoths. But the influence of supermassive black holes extends beyond just gravitational control. In many cases, the material falling into these black holes forms an accretion disk, a swirling mass of gas and dust that heats up to incredibly high temperatures as it spirals inward. As the material gets closer to the event horizon, it accelerates and emits vast amounts of radiation, often in the form of X-rays and gamma rays. This process can lead to the formation of powerful jets of energy that shoot out from the poles of the black hole, sometimes at nearly the speed of light. These jets, which can stretch for thousands or even millions of light years, are some of the most energetic phenomena in the universe. The radiation and jets produced by supermassive black holes have a profound effect on their surroundings. In some cases, the energy emitted by these black holes can trigger or inhibit star formation in the galaxy. The powerful outflows from the accretion disk can push gas and dust out of the galaxy, effectively quenching star formation. On the other hand, the intense radiation can also cause nearby gas clouds to collapse, leading to new star formation. The presence of a supermassive black hole, therefore, has a direct impact on the life cycle of stars and the evolution of galaxies. But how do these supermassive black holes come into being in the first place? This is one of the biggest questions in modern astronomy. One possibility is that they form from the merging of smaller black holes, accumulating mass over billions of years through accretion. Another theory suggests that they could have formed directly from the collapse of massive clouds of primordial gas in the early universe. Shortly after the Big Bang, some researchers even speculate that supermassive black holes could have seeded the formation of galaxies themselves, shaping the early structures of the universe. Despite the progress made in understanding these cosmic giants, the formation of supermassive black holes remains an open question. Current theories suggest that the process may involve complex interactions between gas, stars, and dark matter in the early universe. It's also possible that they could grow rapidly through mergers with other black holes, or by accumulating material from the surrounding environment. However, no single model has yet been able to fully explain the origin of these monsters. One of the most intriguing aspects of supermassive black holes is the role they play in the larger structure of the universe. Their massive gravitational influence can shape the movement of entire galaxies, and they may even be responsible for the formation of galaxy clusters. In regions where galaxies collide, supermassive black holes can merge, creating even larger black holes with greater power. These cosmic collisions, when they occur, can send ripples of gravitational waves through space-time, detectable by instruments like LIGO. The merging of supermassive black holes, though a rare event, is one of the most significant occurrences in the universe, releasing enormous amounts of energy and altering the structure of the surrounding galaxies. As we continue to explore the cosmos, we will undoubtedly learn more about the intricate and powerful role that supermassive black holes play in shaping the universe. Their existence at the centers of galaxies is not just a fascinating quirk of cosmic structure. It is a central feature of the universe's grand design. The more we understand about these black holes, the more we realize that they are not isolated, passive objects, but active participants in the ongoing evolution of the universe. The study of supermassive black holes is still in its early stages, and each new discovery adds another piece to the puzzle. Whether we are tracing the radiation emitted by their accretion disks, detecting the gravitational waves from their mergers, or mapping the orbits of stars around them, these black holes continue to reveal their secrets. What we do know for certain is that they are not just mysterious entities at the center of galaxies. They are powerful forces that help to shape the very fabric of the universe itself. Their role in the cosmic dance is not one of passivity, but of profound influence, shaping the galaxies around them and driving the evolution of the cosmos. One of the more curious consequences of black hole mergers is something called gravitational recoil, a phenomenon that arises when the newly merged black hole is imparted with a kick that can send it hurtling across the universe. This is an unexpected twist in the cosmic dance of black holes, and it's as dramatic as it is mysterious. When two black holes merge, the process isn't always perfectly symmetrical. Despite their immense gravitational pull, the merger itself can cause an uneven distribution of energy, particularly when the black holes have different masses or spins. This imbalance results in a force akin to a recoil that propels the newly formed black hole away from its original position. Think of it like the recoil from firing a shotgun. The force generated by the merging process sends the newly formed black hole flying through space. This recoil is typically small, but under the right conditions, it can be incredibly powerful. The amount of kick a black hole receives depends on several factors, including the relative masses of the two merging black holes, their spins, and the angle at which they collide. In some cases, this recoil is strong enough to eject the newly formed black hole from its galaxy entirely, sending it on a lonely journey through intergalactic space. The discovery of gravitational recoil has profound implications for our understanding of how black holes evolve and how galaxies themselves form. A black hole that is ejected from its host galaxy could be displaced for billions of years, moving across the vast emptiness of intergalactic space. While we can't yet observe these ejected black holes directly, their presence might explain some of the unusual observations we've made, such as active galactic nuclei that seem to be missing their central supermassive black holes. The concept of ejected black holes also has broader implications for the evolution of galaxy clusters. If a supermassive black hole is kicked out of its host galaxy during a merger, the galaxy's gravitational balance is disrupted. This could have long-term effects on the galaxy's structure and, in extreme cases, could even result in the death of the galaxy, a shift in its dynamics that prevents it from forming new stars or sustaining its existing population. Moreover, the ejected black hole might even end up merging with another black hole in a different galaxy, contributing to the ongoing cosmic dance of black hole mergers. In this way, black holes can be part of a never-ending cycle of cosmic evolution, forming, merging, and even being flung into the void to repeat the process. The possibility of a rogue, wandering black hole in the vastness of space raises many questions. What happens to these nomadic giants? Could they eventually encounter another galaxy and disrupt its cosmic balance? Could they even serve as a seed for the formation of new black holes or the triggering of star formation in regions where no such events would have otherwise occurred? The answers to these questions remain unknown, but they remind us of the chaotic beauty of the universe, a place where even the most stable and predictable forces, like gravity, can lead to the most unexpected outcomes. This wandering black hole, ejected, displaced, and seemingly lost, becomes a ghost, drifting through the cold void between galaxies. But like all black holes, its gravitational influence never truly disappears. Even in the silence of its journey, it continues to shape the universe around it, tugging on stars, bending light, and quietly affecting the flow of space-time. And in that sense, even a solitary black hole, cast adrift in the vast emptiness, plays a role in the cosmic drama, a silent witness to the ever-changing dance of the galaxies. The study of gravitational recoil is still in its infancy, and each new discovery will bring us closer to understanding just how these black holes shape the cosmos in ways we never expected. From their birth in the violent death of stars to their quiet, patient drift through the universe, black holes are more than just objects of mystery. They are the architects of cosmic change. The recoil of a black hole after a merger is a testament to the fact that even the most controlled forces in the universe can yield surprising and chaotic consequences. The rogue black hole may be one of the universe's quietest wanderers, but its story is one of profound transformation, not just for itself, but for the galaxies and stars it encounters along the way. Its journey might take it to the farthest reaches of space, or it may merge again with another black hole, continuing the eternal cycle of creation, destruction, and rebirth in the cosmic dance. In the realms of theoretical physics, few ideas are as tantalizing as the concept of the multiverse, the notion that our universe is just one of many, each existing in parallel, separated by dimensions beyond our perception. It's a mind-bending idea, and one that brings us to a mysterious intersection with black holes. Could black holes, these seemingly destructive forces of nature, be the keys to understanding the birth of new universes? The multiverse theory suggests that each black hole, with its event horizon and singularity, might not simply be the end of the line for stars and matter, but could also serve as the beginning of something entirely new, an entirely new universe. This idea arises from the concept of a white hole, a theoretical reverse of a black hole, where, instead of pulling matter in, it expels it outward. If a black hole is a one-way gate to nowhere, could its counterpart, a white hole, be a doorway to somewhere else? One of the most captivating aspects of this idea is the suggestion that each black hole might give birth to a new, self-contained universe. This is sometimes referred to as the black hole cosmology or baby universe theory. According to this hypothesis, the singularity at the heart of a black hole might represent a kind of quantum bridge between universes, where the collapse of matter within the black hole leads to the creation of an entirely new universe on the other side of the event horizon. In this way, black holes could act as seeds for new universes, their immense gravitational forces breaking the fabric of space-time and spawning entirely new cosmic realms. From this perspective, the end of one universe, symbolized by the formation of a black hole, could be the beginning of another. The idea is somewhat akin to the life cycle of stars. Stars are born, live, and die, sometimes leaving behind remnants that continue the cycle of cosmic evolution. In the case of black holes, the death of one universe could lead to the birth of another, each new universe potentially existing in a separate, disconnected reality. This concept is still highly speculative, of course. The idea of a black hole serving as a gateway to another universe comes from combining quantum mechanics and general relativity, two pillars of modern physics that to this day remain difficult to reconcile. Quantum mechanics governs the behavior of particles at the smallest scales, while general relativity explains how gravity works on the largest scales. In the realm of black holes, these two theories clash, as neither can fully describe what happens at the singularity, where gravity and quantum effects are both extreme. Yet, some physicists believe that a unified theory of quantum gravity might one day reveal how black holes could be connected to the birth of new universes. The intriguing possibility that black holes might create new universes also aligns with some interpretations of the many worlds hypothesis, which posits that all possible outcomes of quantum events actually occur, each in its own separate universe. In this framework, every time a quantum event happens, such as a particle decaying or a decision being made, it spawns a new universe where each possible outcome occurs. If this theory holds, black holes could be linked to these quantum branches where the merging of two black holes could act as a cosmic division, creating new realities that exist independently of one another. Even though we can't directly observe these other universes, the idea that black holes might lead to them is a tantalizing thought. If this is true, then every black hole is not just a destroyer of matter, but a creator of realms beyond our reach, places where the laws of physics might differ from our own, where entirely new forms of reality might exist. These universes, birthed from the gravitational collapse of a star or the merger of two black holes, could have entirely different properties. They could have different dimensions, varying laws of physics, or even alternate versions of reality. Perhaps in one of these universes, time moves backward, or the speed of light is different, or even the concept of gravity itself is altered. The concept of black holes as creators of new universes raises profound philosophical questions about the nature of reality and existence. Are we living in a universe that was once contained within the singularity of another black hole? Could there be other beings living in universes born from black holes, completely unaware of the existence of our universe? This idea challenges our very perception of life, the universe, and everything in it, suggesting that the cosmos may be far larger and more interconnected than we can ever imagine. While we cannot yet test these theories directly, the possibility that black holes could create new universes is a powerful reminder of how much remains to be discovered about the nature of black holes and the cosmos itself. It opens up new avenues of research, not just in physics, but in cosmology, philosophy, and even our understanding of consciousness and existence. For now, the idea remains a speculative and thrilling frontier in theoretical physics, one that could change everything we know about the universe and our place within it. Though black holes remain some of the most mysterious objects in the universe, the idea that they might hold the key to creating new realms of reality serves as a reminder of the vastness and complexity of the cosmos. What we know now is only the beginning, and as our understanding of these strange, dark entities evolves, so too will our conception of the universe itself. Black holes, it seems, are not just the end, they might also be the beginning of something far greater. In the immense vastness of space, where galaxies stretch for billions of light years, there are objects that wander, objects that no longer belong to the families of stars or galaxies from which they originated. These are the rogue black holes, solitary wanderers that have been ejected from their galaxies and now drift through the cosmic void. They are not bound to any gravitational system, yet their journey through the cosmos is far from inconsequential. The phenomenon of rogue black holes has become a fascinating subject of study. These black holes are typically thought to be the result of cosmic collisions, particularly during the mergers of galaxies or the violent collisions of supermassive black holes. When galaxies collide, their central black holes often spiral toward one another, merging into an even larger supermassive black hole. During this process, some of the black holes involved are kicked out of the system entirely, propelled by the gravitational recoil we discussed earlier. The result is a black hole that is no longer tethered to the galactic center, but instead is sent adrift, flung into the depths of intergalactic space. Without a galaxy's mass to anchor it, the rogue black hole is free to wander through the void, a cosmic nomad, pulling on the fabric of space-time as it drifts. Yet despite their solitude, rogue black holes continue to exert a tremendous gravitational influence on their surroundings. These nomadic black holes can pass through other galaxies, subtly distorting the gravitational fields of the systems they encounter. In rare cases, their presence can even trigger the formation of new stars or cause shifts in the orbits of nearby objects. Their impact on the universe, though less obvious than the activities of their galaxy-bound counterparts, is profound. They are wanderers, but they leave ripples in their wake, shaping the space through which they pass. One of the most intriguing aspects of rogue black holes is the possibility that they could eventually be captured by another galaxy, though their journeys through the vast intergalactic space may take millions or even billions of years. They might eventually be drawn into the gravitational influence of another galaxy. There, they could merge with another supermassive black hole at the center of the galaxy, continuing the cycle of cosmic rebirth. These mergers could produce intense gravitational waves detectable across vast distances, providing scientists with another tool to study the nature of black holes and their evolution. However, the very nature of rogue black holes raises more questions than answers. How common are these solitary wanderers, really? If they are as frequent as some studies suggest, could they be hiding in the dark corners of space, undetected? By our current methods of observation, are rogue black holes responsible for some of the mysterious gravitational anomalies we observe in the universe, where stars appear to be influenced by unseen forces? And if they are so elusive, could they serve as the dark drivers behind some of the phenomena we still don't fully understand, such as galaxy rotation curves or the distribution of dark matter? Despite these questions, the concept of rogue black holes brings us to a fascinating place in our understanding of the universe. Here, we are reminded that black holes are not confined to the galaxies in which they were born. These cosmic nomads are part of a greater, ongoing journey that spans the entire universe, with impacts felt long after they have left their home galaxies behind. They serve as a reminder that the universe, with all its grand structures and order, is also full of chaos and unpredictability. For now, rogue black holes remain one of the more mysterious and elusive aspects of the cosmic landscape. We can only imagine the lonely, silent journey they undertake through the vast, dark expanse of space, leaving their imprint on the universe in subtle, invisible ways. But in their wandering, they remind us that the universe is far from static. It is in constant motion, full of unseen forces and unexpected twists. The rogue black hole is just one chapter in the universe's ongoing story. A story that unfolds on a scale we are only beginning to understand. Their journey may be solitary, but it is no less significant. They are not mere outcasts. They are agents of change in the cosmos, playing a subtle yet important role in the universe's never-ending dance of creation and destruction. Imagine, if you will, two black holes drifting through the vast emptiness of space, their orbits slowly drawing them closer together. At first, the distance between them seems insurmountable, and their paths appear to be guided by nothing more than the relentless, silent pull of gravity. But as time passes, their paths begin to shrink, each revolution pulling them closer in an intricate, elegant waltz, a cosmic dance that will culminate in a dramatic, inevitable merger. The journey of two black holes on the road to merger is a slow and patient one, unfolding over millions, even billions, of years. In the beginning, the black holes may seem like isolated objects, wandering through the vast expanse of space, each indifferent to the other. But gravity, that invisible force that binds the universe together, has a plan. As the black holes approach one another, their gravitational influence begins to bend the fabric of space-time itself, subtly altering the paths of nearby stars and gas clouds. The black holes are not just moving through space, they are shaping the very structure of the universe around them, their gravitational fields stretching and warping space as they draw closer together. This process is far from a sudden, violent collision. Instead, it is a slow and steady spiral, with each black hole gradually losing energy in the form of gravitational waves, ripples in space-time that carry away the energy and momentum of the system. The closer the black holes get to one another, the more energy is radiated away, and the faster they spiral inward. This inspiral phase is not just a consequence of their gravitational attraction. It is a cosmic dance of decay, a gradual but inexorable journey toward the final act as the black holes near each other. The final moments of their journey become more urgent. The orbits tighten and their speeds increase. The frequency of the gravitational waves grows louder, like the crescendo of a symphony building toward its climax. It is a moment of tremendous energy, where the very fabric of space-time is stretched to its limits. The black holes move ever faster, their paths, drawing them inexorably closer. At this point, the universe itself seems to hold its breath. The two black holes, once separate, now become indistinguishable from one another. Their event horizons begin to overlap, merging into one. And then, in a brief but monumental moment, the two black holes become a single, larger black hole, their combined mass and energy creating a singularity even more powerful than either one could have been alone. This is the culmination of their cosmic dance, the merging of two forces of nature, bound together by nothing more than the unyielding pull of gravity. But the dance doesn't end with the merger. In fact, the aftermath of the collision, the ringdown phase, is just as important as the moments leading up to the merger itself. In this final phase, the newly formed black hole shakes off the imperfections created by the merger, settling into a more stable configuration. The gravitational waves emitted during the ringdown carry with them information about the new black hole's characteristics, providing scientists with invaluable data about its mass, spin, and the details of the merger itself. The road to merger is not just a cosmic waltz between two black holes. It is a journey through time and space, one that shapes the very fabric of the universe. It is a reminder that black holes, though often seen as destructive forces, are also creators of cosmic order. They sculpt galaxies, influence the movement of stars, and even play a role in the formation of new celestial objects. This slow, graceful dance of black holes is a testament to the power of gravity, the force that governs the motion of everything. In the universe, it is a force that shapes not just individual objects, but the very structure of space and time itself. And in the merger of black holes, we see this force at its most extreme, where the universe bends and warps in ways that are beyond our comprehension. Though the cosmic dance of black holes is silent and invisible, it is no less magnificent. Each merger, each Inspiral, is a chapter in the universe's grand story, a story of creation and destruction, of forces that shape the cosmos on a scale that is both beautiful and terrifying. As we continue to study these events, we are reminded of the vastness of the universe and the incredible power that lies within the invisible dance of the black holes. The long road to merger may be a slow one, but when the two black holes finally collide, the energy released is staggering. In that brief moment, the universe itself seems to hold its breath, before letting out a wave of energy that reverberates through the fabric of space-time. And, though the collision is over in an instant, the ripples it leaves behind will echo throughout the cosmos for eons to come. While the dance of two black holes might seem like the pinnacle of cosmic choreography, there is another, even more chaotic and unpredictable phenomenon at play in the universe: the existence of triple black hole systems. Imagine three massive black holes locked in a gravitational tango, their orbits intertwining in a way that defies all expectations. These systems, rare, complex, and highly unstable, are a cosmic soap opera, filled with dramatic twists and turns, where the outcome is never guaranteed in a triple system. Three black holes are bound together by their collective gravity, each exerting influence over the others. At first glance, this might seem like a straightforward case of three objects orbiting around a common center of mass. However, the interactions between three such massive objects are anything but simple. The gravitational forces involved in such a system are immensely powerful, causing the orbits of the black holes to change in unpredictable ways. Their trajectories might seem stable for long periods, but over time, the dynamics of the system can become increasingly chaotic. The gravitational influence between the black holes causes their orbits to shift, pulling them into eccentric paths that grow ever more complex. Eventually, this instability can lead to one of the black holes being ejected from the system entirely, flung out into the depths of space like a rogue black hole. The remaining two black holes, however, continue their dance, now in a new configuration. The ejected black hole, now alone, may wander through intergalactic space, destined to eventually merge with another black hole or contribute to the creation of a new cosmic structure. The dynamics of triple black hole systems challenge many of the assumptions that astrophysicists have made about the stability of these objects. Unlike binary black hole systems, which often follow predictable paths toward merger, triple systems are anything but predictable. Their gravitational interactions create a level of complexity that makes it difficult to model with certainty. In fact, some scientists believe that such systems may not even survive for long enough to allow for direct observation. They may dissolve or collapse into a simpler configuration before we have the chance to detect them. Yet, despite the challenges, the possibility of discovering triple black hole systems opens up a whole new realm of possibilities in our understanding of cosmic dynamics. If we can detect such systems, we may be able to observe the processes that govern their instability, the eventual ejection of one of the black holes, and the dramatic final mergers that result. These systems could provide insight into the fundamental nature of gravity and how it behaves when multiple massive objects interact in ways that go beyond the simple binary model. The interactions between black holes in a triple system are not limited to gravitational forces. The orbits of the black holes can be influenced by the accretion of matter, gas, dust, and other cosmic debris as they spiral inward. This material, while it may seem insignificant compared to the immense mass of the black holes themselves, plays a key role in shaping the dynamics of the system. The inflow of matter can create new gravitational forces that alter the orbits of the black holes, causing them to spiral more rapidly toward one another. One of the most fascinating aspects of triple black hole systems is the possibility that they could be part of a larger cosmic drama, one that involves multiple galaxies and even supermassive black holes. As galaxies collide and merge, the black holes at their centers may form triple or even higher order systems. These systems, when they eventually merge, could release vast amounts of energy, potentially generating gravitational waves that are detectable across the universe. In many ways, triple black hole systems serve as a reminder of the universe's complexity. They are not simple or predictable, but are instead driven by forces that stretch and warp space-time in ways we can barely comprehend. These cosmic soap operas are not just about the black holes themselves. They are a reflection of the larger forces at play in the universe, from the collision of galaxies to the movement of gas and stars. They remind us that the universe is not a static place, but a dynamic, ever-changing system where the interactions between objects can create beauty, chaos, and complexity on a scale we are only beginning to understand. The mystery of triple systems also prompts a deeper question. If the universe is capable of such intricate and unpredictable dances, what other cosmic phenomena are waiting to be discovered? Are there other, even more complex systems out there, just beyond our detection limits, whose dynamics defy the very laws of physics as we know them? As we continue to explore the universe, the soap operas of black holes are just the beginning. of a much larger, more enigmatic drama, one that will unfold over eons with more twists and turns than we can yet imagine. When we look toward the centers of galaxies, we often find something profoundly powerful and mysterious: supermassive black holes. These cosmic giants, which can weigh millions to billions of times more than our Sun, lurk at the heart of virtually every large galaxy in the universe. They exert an immense gravitational pull on everything around them, shaping the very structure of the galaxy itself. But what happens when two of these titanic forces collide and merge? The consequences are far-reaching, affecting not just the galaxies involved, but the entire surrounding cosmic structure. Supermassive black hole mergers are among the most dramatic events in the universe. These mergers occur when galaxies collide, or when two supermassive black holes at the centers of different galaxies slowly spiral toward one another, eventually merging to form a single, even more massive black hole. The process of this cosmic collision is incredibly complex, involving the dynamics of both the black holes and the galaxies that harbor them. One of the most immediate consequences of a supermassive black hole merger is the release of enormous amounts of energy. As the two black holes approach each other, they generate powerful gravitational waves, ripples in space-time that spread outward, detectable across vast distances. These waves carry information about the mass, spin, and orbital characteristics of the black holes involved. The merger itself can also release a burst of radiation, as the accretion disks around the black holes heat up due to the intense friction created as matter is pulled into the event horizons. But beyond the immediate energy release, the merger of supermassive black holes has lasting effects on the galaxy itself. For one, the merging black holes may disturb the galaxy's gravitational balance, triggering the ejection of gas and stars, which can have a profound impact on star formation. In some cases, the energy and matter released during the merger can cause the galaxy to enter a period of quiescence where star formation slows or stops altogether. This is known as feedback, and it can drastically alter the evolutionary trajectory of the galaxy. In some extreme cases, this feedback can prevent further star formation, leading to the eventual death of the galaxy as it exhausts its supply of gas. In addition to halting star formation, the merger of supermassive black holes can have other far-reaching consequences for the galaxy's structure. The gravitational forces involved in the merger can disrupt the orbits of nearby stars, causing them to be flung out of the galaxy entirely. This can lead to a shift in the galaxy's shape and dynamics, creating a more elliptical or irregular structure. In some cases, the black holes merger can even result in the formation of new structures, such as galactic cores with new stellar populations, or the creation of massive galactic halos, beyond the immediate changes in the host galaxy. Black hole mergers can also have broader implications for the larger cosmic environment. For instance, when two galaxies merge, their supermassive black holes can drive the formation of new structures, including galaxy clusters. These interactions can lead to the release of vast amounts of energy, creating large-scale shocks that heat the surrounding gas and potentially influence the formation of new galaxies on an even grander scale. The merger of supermassive black holes can influence the very formation and evolution of the universe. As these black holes merge and form larger, more massive black holes, they contribute to the growth of the cosmic web, the vast network of galaxies, clusters, and voids that make up the structure of the universe. In some ways, these mergers are a driving force behind the continued evolution of the universe, shaping galaxies and clusters as they interact and merge across vast periods of time. One of the most exciting aspects of studying supermassive black hole mergers is the potential to observe these events through gravitational waves. As we have already seen with smaller black hole mergers, gravitational wave detectors like LIGO have given us a way to hear the universe in a completely new way. Supermassive black hole mergers, which occur much less frequently than smaller black hole collisions, are much harder to detect, but their signatures are detectable across even greater distances. This has opened up a whole new avenue for astrophysical research, allowing scientists to study the dynamics of galaxies and supermassive black holes in ways that were previously impossible. The study of supermassive black hole mergers is still in its early stages, and as our detection methods improve, we will likely uncover even more details about these colossal events. Each new discovery adds another layer of understanding to the complex interplay between galaxies, black holes, and the larger cosmic structure. What we know for certain is that these mergers are not just isolated events, they are fundamental drivers of the cosmic evolution, shaping the universe in ways that are both subtle and profound. These cosmic behemoths, once thought of as enigmatic and isolated, are now revealed to be central to the evolution of galaxies and the universe as a whole. As we continue to explore their mergers and the gravitational waves they produce, we will uncover more about the grand architecture of the cosmos and the hidden forces that shape the fate of galaxies, stars, and black holes alike. Gravitational waves are the quiet messengers of the cosmos, carrying with them the echoes of some of the most dramatic events in the universe. These ripples in the fabric of space-time travel across the universe, carrying information about the most violent cosmic occurrences, black hole mergers, neutron star collisions, and even the birth of the universe itself. While these waves may be imperceptible to our senses, they are far from insignificant. They are time capsules, preserving the memory of cosmic events that stretch back to the very beginning of the BAMD universe. Gravitational waves are unique in that they pass through all matter without being absorbed or scattered. Unlike light, which can be blocked or bent by dust, gas, and other objects in space, gravitational waves travel undisturbed, allowing them to carry a pristine signal across vast distances. This makes them an invaluable tool for astrophysicists, offering a way to peer into the heart of the universe's most mysterious and inaccessible events. When a black hole merges, for example, it generates a burst of gravitational waves that ripple outwards, distorting space-time itself. These waves can travel for billions of years, stretching and compressing space as they propagate across the universe. Each ripple carries with it the signature of the event, the masses and spins of the black holes, the dynamics of the merger, and even the distance at which the event occurred. Gravitational waves act as a cosmic fingerprint, allowing scientists to reconstruct the history of these mergers with incredible precision. The beauty of gravitational waves lies in their ability to provide a new way of seeing the universe. Unlike light, which is often blocked or scattered by the vast amounts of interstellar gas and dust, gravitational waves are not impeded by these obstacles. They allow us to observe phenomena that would otherwise be invisible, such as the collision of two black holes or the formation of a neutron star. In this way, gravitational waves are a tool for unveiling the hidden dynamics of the universe, a way of hearing the universe in a completely new and unexpected way. But the reach of gravitational waves extends far beyond the detection of black hole mergers. As more and more events are detected, we are gaining insights into the evolution of the universe itself. Some of the earliest gravitational waves detected have come from the merger of two black holes that occurred billions of years ago. By studying these ancient ripples, scientists can learn about the conditions in the early universe, when the first black holes and galaxies began to form. In a sense, gravitational waves act as a time machine, allowing us to look back into the distant past of the universe, to an era long before light could travel freely through space. Gravitational waves also provide a window into some of the most extreme environments in the universe. The massive energies involved in events like black hole mergers generate waves that stretch and compress space-time itself, offering a glimpse into the very fabric of reality. These waves are so powerful that they can cause measurable distortions on Earth, even though the events that create them may occur billions of light-years away. For scientists, this is a rare opportunity to test the limits of our understanding of physics, to see if the laws of general relativity hold true in the face of the most extreme gravitational forces. As technology improves, so too will our ability to detect these waves. New detectors, like the Laser Interferometer Space Antenna LISA, which will be launched into space in the coming years, will allow us to observe gravitational waves from even more distant and faint events. LISA, in particular, will be able to detect waves from supermassive black hole mergers, providing a unique opportunity to study the dynamics of galaxies and their central black holes. This will help answer some of the most profound questions in cosmology. How did supermassive black holes form? How do they evolve over time? What is the role of these black holes in shaping the structure of galaxies? The study of gravitational waves is still in its infancy, but already it has revolutionized our understanding of the universe. Each new discovery, whether it's the first detection of a black hole merger, the observation of a neutron-star collision, or the study of gravitational waves from the early universe, brings us one step closer to understanding the true nature of the cosmos. Gravitational waves are not just a tool for studying the universe. They are a profound reminder of the interconnectedness of all things, of the way that even the most distant and seemingly unrelated events are part of a greater cosmic story. In the future, we will continue to listen for the cosmic echoes of black hole mergers, neutron-star collisions, and the birth of the universe. These gravitational waves will continue to travel across time, carrying the memory of the events that shaped our universe. And as we study these waves, we will uncover new truths about the nature of space-time, the forces that govern the cosmos, and the mysterious black holes that play a central role in the unfolding drama of the universe. The cosmic echo of gravitational waves serves as a constant reminder that even in the silence of space, the universe is alive, with motion, with energy, with history. The waves we detect today are only the beginning. Tomorrow, as our detectors become more sensitive and our understanding deepens, we will hear the universe's stories in ever greater detail, stories of black holes, galaxies, and the cosmic forces that shape all that is. The universe is telling us its secrets, one wave at a time. To truly understand the enormity of black holes, one must first grasp the profound effects they have on the fabric of time and space itself. These cosmic giants warp the very dimensions of reality, bending time and space in ways that challenge our understanding of the universe. The closer you get to a black hole, the more the familiar laws of physics, the rules we use to measure time, space, and distance begin to break down, leaving us with a universe that behaves far differently than what we experience in our everyday lives. The most striking effect of a black hole's gravity is its ability to distort time. As you approach a black hole, time itself begins to slow down. This phenomenon, known as time dilation, occurs because the black hole's immense gravity stretches and distorts space-time. The closer an object gets to the event horizon, the boundary beyond which nothing can escape, the more pronounced this effect becomes. To an outside observer, a clock near a black hole would appear to tick slower and slower as it nears the event horizon, until it seems to freeze entirely at the moment of crossing. This stretching of time has deep implications for our understanding of the universe. Imagine, for a moment, standing on the edge of a black hole, gazing back at the distant stars. Time would seem to flow normally for you, but from the perspective of someone far away, your movements would appear to slow. The closer you got to the event horizon, the slower you would appear to move to an outside observer, until, at the moment of crossing the event horizon, time would seem to come to a halt entirely. But this isn't just an illusion. It's a consequence of the way space-time itself is stretched by the gravitational pull of the black hole. The black hole's mass is so concentrated that it creates a curve in space-time, and objects near it are affected by this curvature. This is where Einstein's theory of general relativity comes into play. His theory predicted that mass and energy could curve space-time, and the black hole is the ultimate example of this phenomenon, where the curvature becomes so extreme that it distorts the very fabric of reality. This effect is not limited to time alone. The black hole's gravity also warps space. As you get closer to the black hole, distances become increasingly distorted. This stretching of space means that if you were to fall into a black hole, the very way in which you experience distance would change. For example, you would no longer be able to measure the distance between objects in the usual way, because the space around you would be warped by the black hole's gravity. But what happens once you cross the event horizon? The event horizon is the point beyond which nothing can escape, not even light. Once inside, the concept of distance and time itself becomes profoundly altered. In the final moments of falling into a black hole, space itself becomes stretched, so dramatically that it's almost as though the future and the past collapse into a singular point. You might think of the event horizon as a boundary between two very different realities, one in which time and space behave according to the familiar rules of physics, and another in which the laws of physics as we know them break down entirely. As you approach the singularity, the heart of the black hole, where all its mass is concentrated, the gravitational forces become so strong that they create a point of infinite density. The laws of physics no longer apply at this point, and our understanding of space-time breaks down. The singularity is a place where the very nature of reality is appended. Theories of quantum gravity, which attempt to combine general relativity with quantum mechanics, may one day shed light on what happens at the singularity. But for now, it remains one of the deepest mysteries in science. This bending of time and space is not merely theoretical, it has practical consequences as well. Astronauts traveling near a black hole, for example, would experience a different flow of time compared to those back on Earth. A trip close to a black hole could result in an astronaut aging much more slowly than someone on Earth, a phenomenon known as gravitational time dilation. If an astronaut were to travel near a black hole and then return to Earth, they could find that much more time has passed for everyone else, potentially decades or even centuries. The effects of black holes on space and time force us to confront the limits of our understanding of the universe. As we look deeper into the nature of black holes, We are not just probing cosmic objects, we are challenging the very fabric of reality. The mysteries surrounding black holes are not just about the nature of gravity or the behavior of matter under extreme conditions. They are about understanding how time and space themselves can be reshaped, and what that means for the future of our universe. As we continue to explore black holes, we are forced to grapple with the unsettling and awe-inspiring reality that the universe is far stranger than we can imagine. The black hole is a cosmic laboratory, one where the deepest questions about the nature of reality can be asked, and perhaps, one day, answered. It is a place where time slows, space distorts, and the laws of physics break down, offering a glimpse into a universe that operates far beyond the boundaries of our current understanding. The black hole's impact on time and space is a reminder of how much we still have to learn about the universe. It is a testament to the infinite complexity of the cosmos, a place where even the most fundamental aspects of reality can be reshaped by the immense forces at play. After the cataclysmic merger of two black holes, the chaos subsides, and a new entity emerges from the ashes, a single, stable black hole. The final moments of the merger are a symphony of gravitational waves, a violent dance that sends ripples across space-time, but after the dust settles, a calm descends upon the newly formed black hole. This final, quiet state marks the end of the black hole's most dramatic chapter, but it is also the beginning of its existence as a fully formed entity in the cosmos. The newly merged black hole, though born from immense destruction, is a paradox of stability and quiet. It has absorbed the remnants of the two original black holes, their masses now combined into one larger black hole. The event horizon of the new black hole has grown, encompassing a much greater area than either of its predecessors. The singularity, the point of infinite density at the heart of the black hole, remains, but it is now part of an even larger, more complex object. Yet, despite the cataclysmic process that led to its creation, the black hole itself is eerily quiet, almost serene in its final state. This quiet is not just the absence of noise, but the result of the extreme forces at play within the black hole. There is no chaos here, there is no sound, no light. Time itself, as it is experienced by someone near the black hole, stretches infinitely as the event horizon stands as an immutable boundary. But for the black hole itself, the process of settling is remarkably peaceful. It takes a moment to ring down a process where the newly formed black hole sheds any lingering irregularities from the merger, gradually becoming more stable and spherical. In the aftermath of a merger, the black hole settles into its final state. It is now a far more massive object, and its gravitational influence is far-reaching, affecting everything in its vicinity. Yet, the quiet after the storm is not without its significance. The new black hole, now stable, continues to affect its environment in subtle ways. Its gravitational pull continues to shape the galaxy in which it resides, influencing the orbits of stars and potentially regulating the formation of new celestial bodies. The final state of a black hole is marked by a subtle but profound fact. Its influence on the surrounding space-time persists, even if it is now far quieter than it was during the merger. The black hole remains a silent giant, its mass concentrated at its singularity, but its effects on the universe are felt for vast distances. The gravitational pull of a supermassive black hole, for instance, can affect the entire galaxy, influencing the movement of stars, gas clouds, and even the formation of new black holes. Yet, while the black hole may seem to rest in the aftermath of its violent birth, its existence is anything but static. Black holes are constantly interacting with their environments, pulling in gas and dust from surrounding space. In the case of supermassive black holes, they often have vast accretion disks surrounding them, filled with swirling gas that heats up to incredible temperatures as it is drawn in. This process is far from peaceful. The accretion disk can emit powerful radiation as the matter spirals inward. And in some cases, these black holes release energetic jets of particles that can stretch across millions of light years. Even when it seems like a black hole is at rest, its environment is constantly in flux. Its role in its galaxy is not just as a passive object, but as an active player in the evolution of the cosmic landscape. It continues to feed, to grow, and to influence the structure of the space around it. The quiet after the merger is not the end of the black hole's journey. It is simply a new phase in its ongoing existence, a phase of stability before it is once again called into action by the forces of gravity. But despite the black hole's continual influence on the universe, there is something inherently tragic about its final state. The very process that led to its formation, the violent merger, the dance of gravity, the release of gravitational waves, leaves behind an object that is, in a sense, forever isolated. The black hole's event horizon is a boundary beyond which nothing can escape, not even light. Everything that crosses it is lost, swallowed by the darkness and secrecy of the black hole's interior. There is no escape, no return. It is a silent, isolated giant, removed from the rest of the universe, its actions constrained by the unyielding grip of gravity. Yet, in the grand scheme of the cosmos, this quiet state is not the end. The black hole is a force of nature that will continue to shape its surroundings, whether we observe it or not. And in that quiet, it plays a central role in the cosmic cycle of creation, destruction, and rebirth. It remains a fundamental part of the universe's ongoing evolution, quietly influencing the fate of galaxies, stars, and even other black holes. As we continue to observe black holes, we are reminded that their story is not one of sudden endings or dramatic explosions, but of gradual, inevitable processes. The merger of black holes is a magnificent, catastrophic event, but the ultimate fate of the newly formed black hole is one of quiet stability. It is a reflection of the way the universe works, immense forces of creation and destruction followed by long periods of calm and subtle influence. In the quiet after the storm, the black hole remains a powerful, silent presence in the cosmos. As we continue to explore the mysteries of black holes, it is impossible to ignore the deeper questions they raise about the ultimate fate of the universe itself. These cosmic giants, with their infinite density and mind-bending ability to warp time and space, challenge our very understanding of reality. And in that challenge lies the question that has captivated philosophers, physicists, and astronomers for centuries. What happens when time itself reaches its end? The idea of time ending is a concept that stretches our imagination to its limits. According to the current understanding of cosmology, the universe is expanding at an accelerating rate. This expansion, driven by mysterious dark energy, is pushing galaxies farther and farther apart, speeding up the rate at which space itself is stretching. In this ever-expanding universe, the distance between galaxies will continue to grow, and eventually the galaxies themselves will become so far apart that they can no longer interact. Stars will burn out, and galaxies will grow cold and dark. The universe will enter an era of isolation, with only black holes remaining as the lasting relics of the cosmic past in this distant future. It is believed that black holes will play a pivotal role in the final stages of the universe. As stars exhaust their fuel and galaxies fade into darkness, black holes will continue to consume matter, growing ever larger and more powerful. However, even black holes are not immune to the relentless passage of time. Over incredibly long timescales, trillions of years, or even longer, black holes will slowly begin to lose mass through a process called Hawking radiation. This phenomenon, proposed by physicist Stephen Hawking in 1974, suggests that black holes are not completely black after all. Instead, they emit a faint glow of particles due to quantum effects near the event horizon. This radiation causes the black hole to lose mass over time, eventually leading to its evaporation. For most black holes, this process will take longer than the current age of the universe. But eventually, all black holes will die by losing their mass through Hawking radiation, becoming smaller and smaller until they vanish entirely. The death of black holes would mark the end of an era in the universe's evolution. The last remnants of matter, once swallowed by these colossal entities, would finally be released into the cosmos as the black holes evaporate. But the death of black holes is just one part of a larger cosmic tale. What happens next? One possibility is that the universe will continue to expand, growing colder and more desolate as the stars burn out and the galaxies drift apart. This scenario, known as the Big Freeze, predicts a universe in which all matter is stretched so far apart that it becomes isolated and inert, and all energy is used up. The result would be a cold, dark universe, with no stars, no galaxies, and no life. However, there is also the possibility that the universe could meet a much more dramatic and cataclysmic end, the Big Crunch. This idea suggests that the universe's expansion might eventually slow down and reverse, leading all matter to collapse back in on itself. If this were to happen, the black holes would once again become the central figures in the universe's story. As all matter is pulled back together, the universe could end in a singularity, a point of infinite density and temperature, similar to the one that existed at the beginning of time during the Big Bang. The final fate of the universe, then, might depend on the delicate balance between dark energy, dark matter, and gravity. If dark energy continues to drive the universe's accelerated expansion, the Big Freeze might be our ultimate destiny. But if gravity ultimately wins out, the Big Crunch might be the universe's final chapter. In either case, black holes will play a crucial role in the universe's fate, influencing the very structure and evolution of space-time itself until the very end. Even in the quiet aftermath of their own death through Hawking radiation, black holes could leave behind a legacy that lasts forever. The information they have absorbed, the stars, planets, and matter they have consumed, might be encoded in the radiation they emit. This leads to a fundamental question in physics. What happens to the information inside a black hole when it evaporates? This is known as the black hole information paradox, and it remains one of the most unresolved issues in theoretical physics. It challenges our understanding of quantum mechanics, general relativity, and the very nature of reality. But perhaps the most profound question of all is, can the end of time really be the end? Are there ways in which the universe could bounce back from its final collapse, giving rise to new cycles of creation and destruction? Some theories suggest that the universe could undergo a process of cyclical creation, where it repeatedly expands and contracts in a never-ending cycle, with new universes emerging from the ashes of the old dot. In this model, black holes could play a critical role in giving birth to new universes. Just as black holes are believed to act as potential gateways to other realities in multiverse theories, they might also serve as the seeds for the next iteration of the cosmos. The end of one universe might be the beginning of another, with black holes serving as the bridges between them, carrying the history and information of one universe into the next. As we ponder the ultimate fate of the universe, we are reminded that black holes, in all their mystery and grandeur, are more than just cosmic oddities. They are the architects of space-time, shaping the destiny of galaxies, stars, and even the universe itself. Whether as the final remnants of a dying cosmos or as the gateways to new realms of existence, black holes will continue to play a central role in the evolution of the universe for as long as time itself endures, and as we look toward the distant future, to the eventual death of stars, the fading of galaxies, and the slow dissolution of black holes, we are left to wonder, will time itself ever truly end? Or will it simply be reborn in a new form through the eternal cycle of creation and destruction? As we come to the end of our journey through the mysteries of black holes, it's impossible to ignore the profound and lasting impact these enigmatic cosmic objects have had on our understanding of the universe. Black holes, often thought of as destructive and terrifying forces, are, in truth, silent architects of the cosmos, shaping everything around them in ways we are only beginning to fully comprehend. From their birth in the fiery death of massive stars to their graceful yet catastrophic mergers, black holes are not just cosmic anomalies. They are the very forces that guide the evolution of galaxies, stars, and even time itself. In the quiet of space, black holes are constantly at work, bending space-time, influencing the motion of galaxies, and shaping the course of the universe. They are the invisible hands that sculpt the cosmic landscape, creating structure out of chaos, and in doing so, they shape the very fabric of reality. The story of black holes is not one of simple destruction, but of transformation. Each black hole, from the smallest stellar remnants to the largest supermassive giants at the centers of galaxies, plays a crucial role in the ongoing dance of creation and annihilation that governs the cosmos. They serve as the engines of galactic evolution, regulating star formation, consuming matter, and leaving behind only the most fundamental of forces. Through their mergers, they contribute to the cosmic cycle of life and death, marking the end of one chapter and the beginning of another. But despite their enormous power, black holes are not invincible. Even the mightiest of black holes will eventually succumb to the laws of physics, losing mass through the gradual process of Hawking radiation and ultimately fading away. The end of a black hole's life, much like its beginning, is quiet, a slow, inexorable process of decay that will continue over time scales longer than the current age of the universe. And yet, even in their eventual disappearance, black holes leave behind a lasting legacy, influencing the structure of the universe long after they have vanished. As we continue to explore the cosmos and uncover the secrets of these cosmic giants, we are forced to confront deeper questions about the nature of time, space, and existence itself. What lies beyond the event horizon? What happens to the information that is swallowed by a black hole? Can the universe truly end, or is it simply a cycle that repeats itself over and over again? These questions, among many others, remain unanswered, but they inspire us to continue searching for knowledge, to continue pushing the boundaries of our understanding. The quiet power of black holes, their ability to warp space-time, to influence the galaxies around them, and to shape the very flow of time, serves as a reminder that the universe is far more complex and beautiful than we can imagine. It is a place where forces of unimaginable strength and elegance work together to create the world we see and to determine the fate of everything within it. And at the heart of it all, black holes stand as the silent witnesses to the universe's ongoing story, shaping its past, present, and future. As we look to the future of astrophysical research, the study of black holes promises to unlock even more mysteries about the universe, about gravity, and about the very nature of reality. Every discovery, whether it's the detection of gravitational waves or the observation of a supermassive black hole at the center of a distant galaxy, brings us closer to understanding how these mysterious objects operate. The grand design of the cosmos. In the end, black holes are not just cosmic curiosities. They are the silent architects of the universe, forces that shape everything we know, that define the boundaries of space and time, and that remind us of the infinite complexity and beauty of the cosmos. Whether as the final remnants of dead stars or the engines of galactic evolution, black holes remain an essential part of the universe's grand narrative, and their story is far from over.